Je vais te dire dehors que je reprends. Il manque des gens, non? I will start again.
Yes.
Okay. So I will now discuss the kernel methods. So after the linear methods, the kernel methods. And in particular, I will discuss the so-called gap for Gaussian approximation potential. Which is based on the SOAP descriptor. So this was proposed by Bartok and Chani. So there is a paper with Bartok, Kondor, Chani in 2013, and Bartok, Chani 2015. So this is roughly 10 years old. And so the parameterization for the energy is, so as more or less always, we start by writing the energy, the total energy, as a sum of local energies. And then so they, I mostly took the notations from the paper, so that's the, no, I will go back to my notation. So that's E tilde of the configurations. So RKR. And in fact, this will be written as a function of the descriptors, RKR. And this epsilon of the descriptors is linear combinations of the kernel function evaluated on the different configurations of the database. Okay, so here we have a database with configurations Ri as before, I from 1 to the number of data D. And so here, so in general, so Gabriel presented a few kernels, but so I will recall kind of standard things. So examples of kernels are typically, the simplest one would be just taking a dot product between descriptors. So this is, so the kernel function is this K of Ri, sorry. And so basically it kind of gives a way to compare two different configurations. So here the new configurations and the others from the database. Okay, and so the dot product kernel would be just taking the dot product between the descriptors, and then there are other standard kernels, which are the exponential kernel where one would take the exponential minus alpha d1 minus d2 in absolute value or one norm, depending on the size of the descriptors. And then a third typical kernel is the Gaussian kernel. Which is just k d1, d2, which is the exponential minus alpha, and then 2 norm of the norm squared d1 minus d2. Yes.
So there's a k dependence in the capital K kernel, so then epsilon depends on k too, or?
Epsilon doesn't depend on k, but here the descriptor would be for an atomic environment. So so you compare two atomic environments on the same with the same center somehow.
Because you mean it's the k that is in the pertinent atomic environment.
No, wait. No, that there is a problem here. Yeah, you
Epsilon k.
Yes, but it shouldn't depend on k because it shouldn't be so let me think.
That when you call epsilon in the process term, you pass in the descriptor, which is big.
Yeah, you pass it to descriptor.
So it's the same k everywhere.
So
like when you call epsilon first time, the sum over k, you call an atomic environment, and then it's the same in the. I think there's k that's used both for the number of atoms and the kernel.
sorry, what?
The k is both the kernel and the number of atoms, depending on where it's.
Yeah, there's still something that yeah, no, I think that you, so you learn this epsilon of D, and so then somehow in the database you would have all the environments for the K's and the I's. So that would be yeah. So here I would say I would have to check, but I think that here you will have both I, so I from 1 to D, and then you would have the K. So basically you have a database of atomic environment and not a database of configurations. So like every configuration in your database can be seen as a collection of atomic environment, and this is what you put in the fitting. Sorry?
It's a k file data.
Here? Oh, you mean here? This is a function. Okay, this is not the same. Yeah. Okay. Let's put a tilde.
The index in the sum. it's small k I, but that it's not the same as the small k above. Yeah. The first sum.
Yeah, okay. Yeah, okay, I agree. This is different. Yeah. Yeah, so yeah, but the spirit is that you have a database of atomic environment, and then you have the number of parameters that you have in the model corresponds to the number of atomic environments you have. Okay, and so in the gap kernel, so the main idea is to define, so the kernel at the end will be just a dot product with the well-chosen descriptors that were will rely on the power spectrum or bispectrum. Okay, so I will show how it is derived. So as before, so they define a density. So this is exactly the same as before. So a sum of Gaussian functions and then they expand it with spherical harmonics. So we have the same decomposition as before. So sum over NLM CNLM of R GN of R YLM of R hat. So with spherical harmonics and radial basis functions. And then somehow the spirit of the kernel method is to have a way to compare two environments. And so here the idea is to define a similarity between two environments. And this similarity, so we take a density for a first configuration, a density for a second environment, so second configuration, and this we just define it as the L2 integral, so the L2 scalar product between the densities. So somehow this gives a first way to compare two atomic environments. But then what happens is that, so if we have an atomic environment and then we have an atomic environment which is just rotated, what happens is that this scalar product may be very small, while the configurations can be very, very close. So just maybe one example. So we have the center atom here, and then we take either one atom here and then or like, let's say 2 atoms here, and then we just rotate. So basically this rho R will be 2 Gaussian functions centered around these here. And then we have 2 Gaussian functions here. And then if we compute the scalar product between those two, then this will be close to 0. While in fact, we would like something that is reasonably large, because basically this, if we consider up to rotation, these environments are very close. And so the idea here is that they define an invariant kernel by averaging over all possible rotations. And so they define an invariant kernel which is K R R prime, which is defined as an integral over rotation of this similarity function, where we rotate, and just write down the formula here. So this is the scalar product between rho R prime QR dr to some power nu dq. So basically here, what this means is that we consider this this similarity function, but then we consider all possible rotations, and then we integrate this value over all possible rotations. So if I come back to this example, so when I rotate this this environment, so when the two, so there will be values of Q for which the similarity will be very small, but then when they are put on top, basically, then the value will be large, and so overall, this will give me a value defining the similarity, the similarity between those environments that is rotation invariant. And so then what the last step to define the kernel function, so K or K tilde maybe. So then what they do is just that they do they add a normalization step so that the kernel doesn't explode, basically, which is just dividing by the value of the similarity. So you take the similarity, the small kernel function between the two environments, and then you divide by the kernel applied to the same environment and same environment as here. And so this is linked to the descriptors, so the power spectrum that I presented earlier, in the sense that if we take nu equal 2, so the exponent here, so that's basically the correlation order. And so if we take nu equals 2, then the K rho prime is just the scalar product between the power spectrum. So that's just sum over n prime and L of P n prime L P prime n prime L. So basically, if we define a power spectrum P for rho and P prime for rho prime, this is just P dot P prime. Okay, so I will try to prove this. So it can be done. So so let's start with the similarity function here. So we consider two atomic environments, R and R prime, and then we look at what the similarity between those environments. Okay, and so this is by definition just rho R times rho R prime R QR dr. And so here we can basically write down the expansion for the density. So this is just here. And so we expand that. And so we have the sum M NLM, and then we have N prime L M prime L prime. And then we have, so we expand like in a very standard way, nothing really complicated here. The only thing is that, so then the coefficients don't depend on small r, and so then we can just write down what's left in the integral. And so this is the integral of Gn prime r and YL M prime L prime N prime dr. And I forgot the rotation here. Okay, and so we get something like this. And here I assume that the Gn are orthonormal for this scalar product. And so then here, so I perform the rotation. So here I get the Vignode matrix out, as always. And then I get, so some NL M N prime M prime N prime, C NL M C prime N prime M prime. And then okay, so first we can remove the sum over N prime because the N has to be equal to N prime for this to be non-zero. For the L, we get the for the L we have to keep it for now, and so no, L has to be equal to L prime. So here, and then we just expand. So then we have a sum over some M second prime, the matrix of dl M prime M2 prime Q, and then we are left with the integral of Y L M R Y L M prime M second prime R hat the R hat, and so this means that M has to be equal to M2 prime, and so in the end we get the sum over N L M M prime of C N L M C prime N L M prime dl M prime M of Q. Okay, and once we have these, we can actually compute the kernel, the value for the kernel. So here I take nu equal 2, So that's basically, so now I have to compute the integral over Q of S rho R rho Q rho I prime squared dq. And so then, so I now basically integrate. So I have two sums like this. So then it starts being a bit messy with the indices, but I will try my best. So sum over n, L, m, and mu of C, n, L, m, C prime, n, and mu. So basically, I rename this here mu. So that then I would have a sum with no primes and a sum with primes. So n prime, m prime, L prime, m prime, mu prime of C n, L, n prime, L prime, m prime, C prime, n prime, L prime, mu prime. And then, so basically everything doesn't depend, up to here, nothing depends on the rotation. So I can take them out of the integral, and then I get d mu L Q d L m prime mu prime of Q dq. And so this is non-zero only if m is m prime and mu is mu prime. And so this simplifies the sum that we have here. And so then I only have n L, the sum over n L m mu, sum over n primes. That's the only thing that's left here. And then I have, so C n L m, C n L mu, so C prime, and then C n prime L m, C prime n prime L mu. And then I can somehow regroup the terms with C and the terms with C prime. And so this gives me basically the sum over n prime and L of the sum over m of C n L m, C n prime L m times the sum over mu of C prime n L mu, C prime n prime L mu. And so this is the power spectrum Pn n prime L, and this is the power spectrum for R prime P prime n n prime L. And so here, this is just the dot product P dot P prime. So at the end, we recover the power spectrum that was presented as a descriptor. And so, okay, so this was for nu, just erase, but this was for nu equals 2. If you take nu equals 3, then you can do a similar derivation that I will spare you, but you can get the same thing with the bispectrum, basically. And I'm assuming that if you go higher correlation order, you can get the like same, just higher order correlation features in the same way. The same, and you can relate that to the descriptors of ACE using the generalized Clebsch-Gordon coefficients. Okay, so one main advantage of this method is that so the kernel can be evaluated analytically, so it's not it's pretty efficient to evaluate. And in terms of the resolution of the system, then basically it's the same as in the case of the linear method, in the sense that we have the energy at the end is written as a linear expansion of these kernel functions, and the difference is just that the kernel functions are defined from the configurations themselves. And one key aspect here is that basically the number of basis functions is exactly the number of atomic environments you have in your database. And so if you consider a very large database, then basically evaluating the energy online will be expensive because you will have a lot of configurations. And so I know that, for example, this gap potential was used for silicon at some point, in particular by James Kermode and co-authors. And so the thing is that they wanted to calculate the energy of silicon to approximate the potential energy surface for silicon for many phases. So basically trying to accommodate for many different cases. And so they had a very large database. And so due to this, they had a posteriori to sparsify the database to kind of find the best configurations to keep in the calculation of the kernel in order to have an online cost that wasn't too expensive. So this in practice becomes a problem when you have like a very large amount of data, because then you need to choose how to sparsify, and this may not be easy to really find the best configurations to keep in or to remove. Okay, so GAP is one of the methods using kernel method. There is another example of people using a kernel method, which is called SGDML for symmetric gradient domain machine learning. And so this was proposed by Schmila and co-authors in 2017. And this was for the first versions, because then they proposed updated versions of this method, which was actually using neural networks. But the first version of this method was using a kernel method. And so in that case, the descriptors were just interatomic distances. And the kernel is some kind of generalization of the Gaussian kernel. So here it means that they basically take the interatomic distances, which are rotation invariant anyway, and then they do some kind of Gaussian kernel too. So if you permute, so I mean the list of interatomic distances doesn't change, but then I couldn't say on the top of my head how they symmetrize with respect to if they kind of consider sorted distances or if I do something different. At the end, I'm sure they have something that is permutation invariant, but I don't remember how they do precisely. Okay, so that's it for the kernel methods. Are there any questions? if not, I'll now talk a little bit about the neural networks. And so there are really many different methods based on neural networks in this field. And so I will first mention kind of the basic neural networks, so feed-forward neural networks, and then I will move to message passing neural networks. So I think I would say the main reference in this field is really the paper by Beller and Parinello in 2007. So I already discussed the descriptors that they are using, so the symmetry functions, and so now I will explain how they construct the energy from the descriptors. And in fact, they really use a kind of very simple neural network, and so it's quite nice to see the results they got with this kind of architecture. So the first step is similar, same thing as always. So they decompose the energy. So E of R is the sum k equal 1 to capital K of E tilde RK R. So same thing as usual. And so then the question is how they approximate this function. And so for this, they map so the atomic environment RKR to the atomic symmetric function. So that's the descriptors. So that they call so G G1 and yeah, GI1 and GI2. So for the two body functions, and GI2 for the three body functions, so the ones that rely on the angles. And so then the nice thing here is that then the neural network will take these as input, and so the size of the input is always the same, no matter what the system of size is. And so then, so here they use a neural network to compute E tilde RKR. And so what they do is that they use a feed-forward neural network with two hidden layers, and let me check. So they have like very few, 40 nodes for each layer. So that's I mean, that's pretty small for a neural network. In the end, they have about 1,000 parameters. So that's, I mean, for a neural network, again, that's reasonably small. And so somehow, if we want to draw a picture, so we have the input layer. So we have the so GI1, so the G1 to G1 alpha, and then we have, so that's the two body functions. Then we have the list of three body functions. G2 beta. And so this is basically the input of the network. And then there two hidden layers. So here, so it's fully connected. So it means that everyone is connected to everyone. And then there is one output, which is the E tilde. And so they use the hyperbolic tangent as an activation function. And so basically in the end, so if we write the F FA as the activation function, then let's say the parameterization can be explicitly written, and it's just, so this is the E tilde, and it's, so FA squared 0, 1 squared plus the sum J from, yeah, no, that doesn't work. No, I won't write it. Sorry. But so it's kind of here. What happens is really that you start from the input, and then you have two compositions with the weights and the biases, and then you have as an output the energy. And so in the end, so yeah, I said that you have, in that case, about thousands parameters. So this is pretty low, but still, I mean, when you want to train the neural network, so then you write down the cost function, which is still the mean square error on all the configurations, and then this is a nonlinear method. And so you cannot just solve a linear least squares problem. You have to solve this using other techniques. And so in that case, the training time can be long. Basically, that's one of the drawbacks of this. And but one nice aspect is that the evaluation cost doesn't depend on the number of training data points. So this is a key difference, for example, compared to kernel methods. In kernel methods, the evaluation cost of the energy depends on the number of training data points, while here, once you have, basically you have trained your biases and your weights and biases, then basically you just have to compute the descriptors first, which, I mean, you saw yesterday, it's not that difficult to do, and then compute the two compositions, and then you're done. So this is very fast. Okay, and so in the field, there are many different methods that use already architectures close to this. And so so for example, the ANI, so they also use some kind of symmetry functions as descriptors that they feed to a neural network. So the reference is Smith, Isayev, Wattberg, 2017. And so what they did, so so Beller and Parinello, if I remember correctly, they did it for silicon. So they only had one atom type. And so in ANI, they consider molecules. So they have to take into account the chemical species. And so what they do is that they train one neural network per atom type. So basically, when the center atom is of a given type, there is an attached neural network to that. So they have, yeah. So at the end, they have more parameters, of course, because of this. And they also have like 3 to 4 hidden layers. And to give you an idea, so typically the layers can have between 32 and 128 nodes. This is somehow for the first versions, because then, I mean, in these methods, there are usually like a series of papers with like updated versions, going for more complicated systems, doing different applications. And so the architecture is not fully fixed. And so depending on the paper you're looking at, the sizes and the number of parameters may be very different. But this is what is presented in this paper. And yeah, and then another potential using feed-forward neural network is the DeepMD. So this is 2018 by Zhang and co-authors. And here they have, they don't really use symmetry functions. They have kind of 3-body descriptors. They call them local frames. And here I haven't fully understood how to really build those local frames in a systematic way, but anyway, they start from descriptors, and then they kind of similarly to here, they use a fully connected feed-forward neural network. And here in the version I found, they had like 5 hidden layers. And then the size of the layers were, for example, so 2, 40, 120, 60, 30, and 10. So that was kind of the number of neurons per layer for the 5 layers. So this would mean that you start from the descriptors, then you have here 240 nodes, 120, 60, 30, and 10. So to be honest, I'm really not an expert on that. So I have the impression that in all the papers I read, this was the case, but I couldn't explain why. But I don't really know.
So that's maybe because we have a single output.
Yeah. Input. Possibly, yeah. Okay, so now I will try to explain message passing neural networks. And so in particular in the context of potential energy surfaces. So I found a very nice reference by Gilmer and Carthus. So that's people from Google, where they explain kind of in an abstract way what a message passing neural network is. And so it's pretty clear. And okay, so so the main idea behind message passing neural network is to take into account the 3D structure of the molecule to build the neural network. So somehow we forget about the first part of pre-building descriptors and as an input to the neural network. at the input of the neural network, we will really have the atomic positions, but then we construct the network differently so that we keep the information of locality. So we will take into account when the different atoms are close to each other. And so okay, so the first thing is that the molecule is seen as a graph. And so basically we will consider links between the atoms if the atoms are within some cutoff radius. So we need here some cutoff radius. And so basically if we have something like that, we can imagine that those three can interact, and this one is too far from anyone to interact. Okay, and so then, so each atom is characterized by a list of descriptors. So each atom is characterized by a list of things. So first, the position. So something that I will call sigma I of t, which is I, zi, hi of t. Okay, and then so t will be an index that will somehow move through the network, and which basically this will be updated at each kind of layer. But this layer are the message passing steps. So I will keep this. Okay, and so then there are basically two main steps. There is something that is called message passing. And so a message passing step, and then a so-called update step. So this gives what happens when we change t. So basically, we construct a message. So the message function is called m. And this message function consists in summing over all the neighbors of the atom I of some message function, capital M, which has to be fitted and which couple two sets of descriptors. And then we have the update step, which consists in updating the descriptors with some function that is called ut, sigma it, and mit. And so this is also a function that has to be learned. And the last step is the readout. And the readout is just at the end to compute the energy. Here we sum basically over the different steps, some readout function that also has to be fitted of all the different descriptors. And this is basically for atom K. Okay, so then let me try to explain it somehow on a graph. So, and maybe somehow a way to see it is to consider a hydrogen or like an atomic chain, because then the molecule can be seen in 1D, and then I can take that somehow similarly as an input, and I will, let's say, have let's say that this is my molecular graph. So this is my molecule, and so basically here at step 0 I have, so let's say here I have 5 atoms. So here I have sigma 1 0, which is just R 1 Z1 H1 0. Then I have the same for so this is sigma 2 R2 Z2 H2 0, and then and so on up to sigma 5 0 R5 Z5 H5 of 0. And then basically to get to the, so this is basically T equals 0. And then you go to T equals 1. And so T equals 1, you still have 5 atoms, basically. So somehow the number of nodes here doesn't change. But also, maybe I should mention this. This is kind of a super nodes, because here we have descriptors. So this would be somehow kind of a vector with R1, Z1, and then all the features. So R1, Z1, and then H1, 0. Okay, I should put it, write it bigger. So here, R1, Z1, H1, 0. And so this is the same for all nodes. So basically for atom 1, I have these descriptors characterizing it. Then for atom 2, I have the same thing, and so on. And then to go from T equals 0 to T equal 1, what I do is that so I do the sum over the neighbors of these functions, of this message passing function. So basically I mix the sigma i's, and so here I mix only the atoms that are close together. So here, for example, this atom will only interact with this one. So here I will only have information going from this one and this one. Then for the second one, I will most likely have something that depends on these 3 atoms, and so on. And here I took the simplest case where I imagine this as a kind of a chain where only like nearest atoms interact. So the cutoff radius is chosen so that the atoms that are at 2 distance are too far to interact. And so here, basically this is the first step. So I sum over the neighbor of this function here. And then I update the H1, the H, so this part of the descriptor, with some function that depends on both the sigma I, so or everything here, and the message function. So somehow you can see it as a mix, so as a capital F function that depends here on F1 sigma 1 0, sigma 2 0. Then here this is a F sigma 1 0, sigma 2 0, sigma 3 0, and so on. Okay? And so this is for t equals 1. Then I go to t equals 2. And so then this F gives us the same structure as like I have still R1, Z1, but here I have H1, 1. And so then I have t equal 2, so then I still have the same, basically the molecular graph doesn't change. And then I do the same kind of update. So at the end here, I will have F, so maybe G, may be different, but sigma 1, 1, sigma 2, 1, G, sigma 1, 1, sigma 2, 1, sigma 3, 1, and so on. And so what you see here is that while you go through the different message passing steps, you see that the descriptors here, they depend on more and more atoms in that are further and further away. So here, even though I said the cutoff radius is such that only nearest neighbors interact, when I'm here, I already have second nearest neighbor that interact in a nonlinear way through these descriptors at the step t equals 1. And so, and the last step is the readout. And so basically, this is, so I have here 5, so still 5 local energies to compute. So that's the E tilde k. And so basically what is done is that I take a function. So here, maybe I use another color, but I have a readout function of that depends on this sigma 1 0. So this would be sigma 1 1. And so I do I compute RT of sigma k 0. Then I compute RT sigma k 1, and so on. And I sum them all. So this kind of this readout step is written here in the kind of most general way, and I will show you in the different implementations that exist that in general this readout function is a bit simpler than this generic version. But so here we would have RT sigma 1 0 plus, so R0, then R1 sigma 2 0, and so on, plus R. And so the last step is usually denoted by a capital T, sigma T, no, sorry. This is sigma 1, 1, and then sigma capital T of 1. So I always take the descriptors of the first atom, and then I I sum over all of them in some nonlinear fashion because I have the readout function here. And so, I mean, I like to kind of see it with a layer wise, but I think what you can also imagine is just taking the molecular graph. So you have the atoms somehow that will interact within some cutoff. And then you somehow stack up the layers. So you have at t equals 0, you have descriptors. Then you transform them by switching, by combining them with the neighbors, and that's kind of where the message passing name is coming from. And then you have your molecular graph with new descriptors at t equals 1. Then you mix the neighbors again, you go to t equals 2, and so on up to t equals capital T. And then you sum in some nonlinear way to get the local energies. Yes. Okay, so that's what comes next, because it's really then it really depends on the method. So what are the parameters in this? So first, what are the hyperparameters of these models? So, or what is learnable features? So what you have to choose are the number of layers, the cutoff radius, and then, of course, you have to parameterize the message function, so MT. You have to parameterize the update function. And so UT, and you have to parameterize the readout function, RT. Okay, and so this is used in actually many different methods. So I give, I don't have all the references, but I give you a few names. So for example, deep tensor neural network is a message passing neural network. SNET, I will talk about it, is also a message passing neural network. PISNet, DimeNet, Pi, and N. So there is really a kind of a zoo of all these networks. GemNet, Nequip, I will discuss it. MACE. And so, yeah, so I was planning to talk to you about DTNN, SNET, Nequip, and MACE to kind of, so just to give you an idea of what are these functions in these cases, and so how these methods are different. And so this, I would say, is kind of the more recent compared to kernel method or linear methods. So this, I would say, has been highly developed in the, let's say, last 5 years or so. Okay, so yes.
So if I have a new configuration that I want to predict,
Yes.
do I just shove it in the neural network and ignore it?
What?
I have like a new set of causation.
Yes. Yes, because it's invariant with respect. Yeah. No, it's just yeah. It is because you learn the message function. You learn only basically this, and this. And also, I mean, how you compute the sigma I, but kind of the basic one. So once you have a new configuration, you just apply these steps. And so this you can
Add more nodes or something like that. But as long as we keep
so you have more nodes, but somehow when you code that, you don't write it as layer wise. You just do a for loop over the t's, and then since you have the MT and the UT, then or an RT, then you're good. Somehow that's it. Okay, so. So the first message passing neural network I want to discuss is deep tensor neural networks. And so this was proposed by Schütt and co-authors in 2017. And so here the message function is some kind of very small neural network, but like very, very basic, just one layer. So it's just a hyperbolic tangent of W0, W1, H, WT plus B1 times W2, E, VW plus B2. Okay, and so W0, W1, W2 are matrices. So here you can really think of as a feed-forward neural network. So that's the weight matrices. And B1, B2 are vectors. And so here that's the H that is here. And so basically you do some kind of nonlinear transform on the H that you multiply by this, which is the length between so this is so maybe I should write it R. So it's the interatomic distance between V and W.
what is HW?
HW is it's what's inside here, the descriptors. I mean sorry?
Why is the word W?
So yeah, okay. It should be I mean it's just that okay, so it should be I and J if you want. IJ. If I go back, so maybe I write it here, so you have MT of sigma IT, sigma J T. So that's the most generic thing. And so here, what happens is that it only depends on HIT and the interatomic distance here. And because you only use the interatomic distance here, I believe this is permutation invariant and rotation invariant. I mean, mostly rotation invariant. That. Okay, and so now so I will kill this, and then let's erase this. And so here, the update function. So here you see maybe I put a color on the weights on the parameters that you have to fit. So in that case, what you have to fit are the matrices W0, W1, W2, and the biases B1, B2. Okay, and so now the update function is fixed. So here in that case, you don't have to learn anything at that stage. And so ut sigma I t mi t is actually just the sum I t plus mi t. So this is just a sum. So pretty easy to write. And then the last step, the readout function. So here it's a particular case of what I wrote before. There is a part that is learned, but basically it only depends on the capital T. So we forget basically what happens on the previous layers, and then they use a neural network that will take as input the HIT. And yeah, and I couldn't say how many layers they use here. Probably not so many. And so in that model, they use 3 message passing steps. So that means that capital T is 3. And that's also, that's also a key point of these message passing neural networks. You cannot afford too many steps because the computational cost grows quickly in terms of the capital T that you're using. Yes?
In capital T and layers?
Capital T would be the number of layers. Yeah. Oh, yeah. That's yes. It's just that people don't. I don't think that people use the name layers for message passing neural networks. So you just say message passing steps. So, but in this representation, this is the number of layers. Oh yes, that's what I said. So in that case, in the most generic version, you sum over all descriptors at each step with a possibly different function. And here you just take the last one and you take a readout function on the last one. The sum over R I is probably just because you get the total energy, and so this should be removed. I mean, somehow if you, yeah. Sorry?
You have written like K tilde is equal to
yes, exactly. Yeah. So it would be EK tilde. In that case, would be just a neural network of H K capital T. So this is perhaps this is T equals 3. Yes.
So here you update HT plus 1 with this update function. So it's just a function that brings information all the way, but you have to initialize the HT.
Yes.
You compute HT plus 1 from HT.
Yes.
You take that 0 or
this I will check tonight. Because yes, I am assuming this as a yeah. Yeah, I mean, I'm guessing that the initialization has an influence, but yeah.
It's just a way to carry some information, even though it's hardly interpretable.
Yeah. Yes?
So another question, you said that we don't want to have too many layers because the function is
right.
But here it seems like it's just linear, so not number.
I mean, it depends on what you put as a message function and and the update function.
Because here the coefficients don't depend on, for this one. I mean the W012.
Here, actually, that's a good point. I would say they depend on T.
Okay.
So you would have like for each layer, you would have different weights. But in principle, they don't depend on the atoms. So that's just
If you have more layers, you have way more coefficients than.
yes. And it also depends on the size of this this H. Which could be large in principle. Okay, so should I stop here? I can maybe, and so I'm done with this deep tensor neural network, and so tomorrow I would still like to talk about SNET, NeQuip, and MACE, kind of in the same setting. Thank you.